Okay, good evening, everybody. Um, Thank you for taking part in that activity. So, that activity is meant to kind of help you feel out where your chemical intuition is at. Chemical intuition is this idea of looking at chemicals and saying something feels off. For instance, those of you that were on the back left problem, you looked at an O-tenesium bond and you said, what the hell is tenesium? I didn't know that was going to come into play when I was actually abbreviating a group. And we'll talk about this more in coming chapters, but rather than drawing out this structure, I abbreviated this as OTS. Oh, shoot, I forgot my sulfonyl group. I abbreviated this part of the structure as TS because it's a tosylate compound. There's some common nomenclature in there. Nomenclature you really don't get into much until OChem 2. The benzene with methyl is called toluene. Benzene with a sulfonyl group, the SO3, is called sulfonyl benzene. So together they're tosyl. Anyways, that was just an abbreviation for a structure. But what you guys did in the back was a substitution reaction. So a bond between carbon and a group broke before a bond between carbon and a different group formed, and then there was just an acid-base process at the end. Those of you that were back here, you were looking at an elimination reaction, acid-catalyzed dehydration, where first sulfuric acid acted as a strong acid and protonated an alcohol group. And then the CO bond of the alcohol broke off, which essentially just made water that floated away. And then the positive charge that remained on the carbon got removed because the sulfuric acid's conjugate base, bisulfate, took away a hydrogen, which helped form a carbon-carbon bond. That was our elimination step. And then up here, we looked at an addition reaction. This was only 2 steps, as opposed to those which were all 3 steps, 2 intermediates. And at first, this group had convinced themselves there were 2 intermediates, 3 full steps. And a little bit of chemical intuition said something feels wrong about one of these steps. In one of the steps, I'm forming a CBr bond and at the same time breaking a CH bond to make a C- group. Something feels wrong about needing to do that just to undo it going forward. And that's one thing that I want you guys to develop is a sense of chemical intuition. This doesn't look like anything we've seen in class. This doesn't seem like something an acid should be doing. Right, at one point, this acid-catalyzed dehydration, they protonated sulfuric acid using an alcohol, which is a very hard thing to do. But an easy mistake when it's an option and you just say, I don't know, maybe the atoms are there, the charges are balanced, there's nothing technically wrong about it. But then you think about, what does sulfuric acid do? Does sulfuric acid take protons? Never, right? That's chemical intuition. It's very hard to describe. It's very hard to refine. But the more time you spend in chemistry and thinking about chemicals, that's more of what you get is chemical intuition. Okay, I wanted to wrap up this worksheet that we were looking at last week. Again, kind of talking about chemical intuition. By the way, did we end up drawing arrows on this completely? Did we finish all the arrows here? Okay. I'm just going to repeat it for the sake of what we had. We recognized that in this first step of this mechanism, there are 2 possible intermediates, and yet based on the product that we see, there's only one thing that happens in that second step. Only one of those intermediates reacts, which means only one of those intermediates must form. In this reaction, based on the final products, I can see that I need water to bond to a hydrogen. I need bromine to take electrons from carbon. And the only way I can get a hydrogen for my water is if I take one of the hydrogens from these methyl groups. So by forming an OH bond, I'll have to break a CH bond. And by breaking that CH bond, who owns the electrons in a CH bond? Carbon. Carbon can then take those electrons and share them with the carbon that lost electrons because bromine left. So one question that we have to ask ourselves here is, does it happen all at once? Water takes a hydrogen, bromine takes electrons, and the carbon-carbon bond forms? Well, if I know that there's an intermediate, then I know it can't all happen at once. I'm going to have to form something and then do another step. Okay, well, what seems more plausible? For water to take a hydrogen off of carbon and leave carbon with a negative charge, and then break off the bromine? Or would it make more sense, and I'm sorry, I'm not going to draw in the arrows yet. Would it make more sense to break off the bromine and leave carbon with a positive charge, and then steal one of the hydrogens to make the carbon-carbon double bond? Only because we know there's an intermediate. Otherwise, there is that third option of everything happening at once. But since we know there's an intermediate, which of those two intermediates seems more plausible to you? Discuss your chemical intuition. Elliot? Have you seen carbon with a positive charge?
Yeah.
Where? Literally right above it?
Yeah. Like often.
Yeah. Have you ever seen carbon with a charge before this class? I can think of two instances. Cyanide and carbon monoxide. Both of which, by the way, poison you from the inside out by binding to the iron in your hemoglobin. That's probably the only time you've seen carbon with a charge before this class. And look, they're both carbons with negative charges. And then since coming into this class, I have shown you carbon with positive charge a number of times. Early on, when we looked at electron arrows back in Unit 2, I showed you how carbon can have bonds that break and leave the carbon with a positive charge. This group back here, you had an OC bond break, leaving carbon with a positive charge. This group back here, you had a CO bond break, leaving carbon with a positive charge. Here, you had a carbon-carbon bond break, leaving carbon with a positive charge. All three of these mechanisms had an intermediate where carbon had a positive charge. So chemical intuition says, I forgot something here, didn't I? I forgot my positive charge on the carbon. We don't see carbon with a negative charge often. We see carbon with a positive charge much more often. So the bottom one seems more familiar. Here's another way to think of that. How good of an acid is carbon? How well does carbon give away its protons? Not very well at all. An sp3 hybridized carbon has a pKa in the 50s to 60s, which means if it does act as an acid, if it takes on a negative charge, it is an aggressively strong base. And how good of an acid is H3O+? Very good. That has a pKa like -3. Water has a pKa around 15.6. So pKa of 50 versus pKa of -3, this equilibrium doesn't exist. This never forms. And you can lean back on your pKa strength, but you can also check in with your chemical intuition. When does carbon ever act as an acid? Very rarely. So based on that information, we learned something. This must be the intermediate. First, the carbon-bromine bond breaks. Electrons have to go to the bromine because bromine owns those electrons. That leaves me with carbon with a positive charge, bromide, and water. So then second, a lone pair from oxygen binds to the hydrogen. I'm going to redraw this in a better color. And up here. The oxygen binds to a hydrogen. In this case, it doesn't matter which. They're all identical. And the CH bonds, which are owned by the C, carbon owns those electrons. Carbon takes them and shares it with its electron-deficient neighbor, making a carbon-carbon double bond. Okay, this is not something that I'm going to have you memorize right now. Instead, this mechanism comes back in Unit 5. But the mechanisms that I will ask you to show me on exams, we will go through. We'll go through the steps. We'll name the reactions as well. So you won't have to guess about how many intermediate. Well, you may have to figure out how many intermediates. But you won't have to guess what the steps are to the reaction. Those are things we're going to work on. This is just an overview of what mechanisms will look like. You guys recognize on your unit test, you had to fill in arrows on your unit test. On your midterm exam, you had to fill in arrows and predict the product based on arrows. And those were actually 2 steps of a mechanism. On the final exam, you'll just be shown starting material and product and asked to show the mechanism. That's kind of the step up that the midterm was supposed to give you. Here are 2 steps, fill in the blanks, and on the final, it'll be decipher it.
Why are you drawing them just the one hydrogen? Is it just to show where the electrons are going?
Well, I'm not going to waste the time to draw all 9 of them because 8 of them are not changing.
So you're just drawing in the one that is changing?
Yep.
Okay.
I'm showing a
Just
relevant
wanted to
hydrogen.
clarify that. Okay.
And I have to at least draw that one because I can't show a bond breaking without the bond being visible.
Okay. I was just wondering why you were drawing any of them, but that makes sense. Okay.
All right. Today, we're moving on to talk about alkenes. And so this is that new worksheet that I passed out while you were all working, but I don't think I got everybody. Who did I not get? And I've got this for you. Can we have a little discussion? What alkenes do you guys know of? Any? I was like, how did you get it? I know some of you know alkenes because you've done your organic molecule analysis of an organic compound and you have alkenes in it. My ears are open. No one in this room has alkenes in their compound, or you forgot.
Okay. This is the one question I did have for you.
All right.
Is it an alkene if it's in the benzene ring?
No.
Okay. So that's fine.
Thank you for asking. The aromatic ring does not have alkenes in it. In a similar way, the carboxylic acid does not have an alcohol. Amides do not have amines.
That's what I thought. Okay.
Esters do not have ethers. Okay. Well, then let's take a step back. Can we define an alkene?
was doing homework and I typed in propene on accident instead of propane.
There you
So
go.
it's an alkene.
Propene is an alkene. Good. Propene is probably not an alkene you've ever come across. Propane gas you've probably used before or have known people have used, but propene probably haven't used.
I was really confused.
Yeah. One letter makes a big difference.
That it does.
How can we define an alkene?
At least one carbon-carbon double bond.
Yeah, these are carbon-carbon double bonds. Technically, you don't need to have any sort of hydrogen requirement to be an alkene. They can be bonded directly to halogens, alcohols, whatever. And we'll clarify, Will, thanks for bringing this up, the aromatic ring does not have alkenes. Things that are attached to alkenes are called vinylic. Good example here is vinyl chloride. Vinyl chloride is a precursor. Oops, drew that in the wrong spot. Vinyl chloride is a precursor to polyvinyl chloride, PVC, like PVC piping. The plastic is a polymer of vinyl chloride. We call it vinyl chloride because the halogen is connected to the alkene. That's a vinylic halogen. On your spectroscopy assignments, on your correlation table, we say that the sp2, on the NMR correlation table, we say that the alkene region is this vinylic proton region. Those vinylic protons are attached to the alkene. And we can describe alkenes by their degree of substitution. The difference between describing an alkene by its degree of substitution and just a regular carbon is that the alkene needs to be described by two positions. So, of course, we could have a non-substituted. That would just be the compound ethylene. And listen, I don't know who was in charge of naming this guy. They could have named it ethene based on nomenclature rules, but they named it ethylene. Non-substituted. Of the two carbons in the alkene, neither of them are bonded to other carbon groups. Monosubstituted. Here's a compound that's often called 1-butene. I don't know why I said often called, that's its name. Two carbons of the alkene, how many carbon groups coming off? Just one. Here's the one carbon group. And then a hydrogen, a hydrogen, a hydrogen. Inevitably, I try to make this make sense every semester, and somebody is confused about how to identify the substitution. So whether you look at it as how many hydrogens are coming off, and then the inverse of that, or whether you look at the two carbons of the alkene and you figure out where there could have been hydrogens, but there aren't because there are carbon groups, I don't know. Try to figure out a way to recognize this is the 1 degree of substitution for the alkene because there are hydrogens everywhere else. At di-substituted, we actually get two different versions. We can have a version that has two carbon groups coming off of the same carbon of the alkene, and we can have a version that has one carbon group coming off of each. Tri-substituted and tetra-substituted. Much more straightforward. Of the two carbons of the alkene, tri-substituted has 3 carbon groups coming off. Just one position connected is a hydrogen, or really a non-carbon group. And then tetra-substituted, all 4 positions coming off of the alkene are carbons. Let's apply this real quick. We've got some structures we're going to learn how to name. First, we're going to talk about this MO diagram, but I want you guys to just look through this list of compounds and label them. Are they mono, di, tri, or tetra-substituted alkenes? Are there any that you look at and you're just not sure how to assign it with its substitution? Too bad they're not numbered. All right, how about this? Let's move it from an individual activity to a board activity. Anybody feel brave enough to pick a compound and label it as mono, di, tri, or tetra? Or call it out and I'll write it on the board for you. You went all the way to drawing it.
No, I did not.
You didn't draw it.
No.
Do you want to do any of these?
Sorry, I was thinking the one in the middle next to it. Is
This
die.
one?
No, right above it. Above that one. Is die because it's on the board. And,
Yeah, you're right.
so, there we go.
Good job. Kiara.
The first, that one, I was in die.
Also die. Good.
Question.
Yes.
Does it have to go, like you're counting like the branches coming off, does it have to go to another carbon? Or like when it goes to, let's say like the ME on the second one, does that count?
Ah, what is ME?
Is that a metal?
That's methyl. That's CH3,
Okay, okay.
which is a carbon. Thanks for bringing that up.
Okay.
Yep. So what would you call this one?
A try.
Try. Give me another. I think there's enough. No, not everyone could do it. Nicole? Where? Underneath it? Here? Got it. Good work. What else?
So the next one down, since there's two, was that spot in between the two count double or just single time?
Yeah, it counts both. You'd have to describe both of them.
Okay, and then you add them together?
No. They're two separate alkenes.
Separate names.
Yep, so you're going to name them separately. Or describe them separately. They're both di. Yes. Also di. Yep. What about here? Mono. And here? Also di. A lot of di substituted ones. Oh, what about below it? If it's not a carbon group, it doesn't count as a degree of substitution. Just like what we had when we were talking about regular carbons, right? You can have a tertiary alcohol, which means a carbon bonded to 3 other carbons and an OH. The O doesn't count as a degree of substitution. Neither does the halide here. So this is also a di-substituted alkene. You could call it a di-substituted vinylic halide. And my last one.
That's try, right?
Tri-substituted. Okay. I also wanted to remind you that there are types of alkenes. One of them is called the cumulated diene. I think actually this is not just types of alkenes. I'm sorry. This is types of dienes. Accumulated diene is one where 2 alkenes come together at a single point. 1 carbon that is a part of 2 different alkenes. It's a very strange functional group. The pi bonds in either directions are perpendicular to each other, which means they have no resonance with themselves. They don't have any resonance with each other. A more common type of diene is called a conjugated diene. Conjugation is this idea of an uninterrupted series of unhybridized p orbitals. That's what allows for resonance. Resonance is delocalization or movement of pi electrons, electrons in p orbitals. And so to have resonance, you need an uninterrupted series of p orbitals. That's conjugation. So this would be an example of a conjugated system. Here's another example of a conjugated system. Uninterrupted series of sp2 atoms means an uninterrupted series of p orbitals. Resonance is allowed through those systems. Is this limited to dienes, by the way? Could you have a conjugated triene or a conjugated tetrene? Just keep adding carbons. Keep adding alkenes in series, and you can conjugate a very long structure. And then the last saddest type of diene is the isolated diene. The isolated diene has some sort of sp3 hybridized atom in between its alkenes. sp3 atoms, being fully hybridized, cannot participate in resonance. They have no unhybridized p orbital to engage. So isolated dienes, different character than conjugated dienes. Different types of reactivity allowed. All right, so those are our different ways that we describe alkenes. When we look at alkenes, we describe them by their substitution, and we describe them by their connectivity, especially if they're dienes. Are they isolated? Are they conjugated? Are they cumulated? All right, now to the worksheet. So that we can understand a little bit better the molecular orbital diagram. Remember that in molecular orbital diagrams, we are showing 3 lanes. On the outer lanes, we're showing the atoms that hybridize together, and on the inside, we're showing the new orbital that exists over that species. So here, I'm looking at an sp2 carbon and an sp2 carbon. Those are my outer lanes. How many sp2 orbitals on an sp2 carbon? 3. sp2, 3 orbitals needed to hybridize, 3 orbitals created. How many of those orbitals are actually used in the carbon-carbon double bond? One of the hybridized orbitals creates the sigma bond between them, and the unhybridized p orbital creates the pi bond between them. What we're looking at on the left and the right hand side is the sp2 and the p orbital that are required to create the carbon-carbon double bond. We're ignoring the other 2 sp2 orbitals that are bonding to the other things. Bonding to the halogens, bonding to the hydrogens, bonding to the carbon groups, whatever. And by the way, this is what your hybridized orbital kind of looks like. One big lobe, one smaller lobe. When these hybridized orbitals overlap constructively, we do not have a hybridized orbital anymore. We don't have an atomic orbital. We have a new molecular orbital, an orbital that envelops 2 nuclei. This is what that orbital looks like. The nuclei are close to those nodes, but we call it now a sigma orbital. And of course, assuming that each carbon brings 1 electron each in its hybridized and 1 electron in its p orbital, we can say that the sigma fills and this new pi fills. The pi orbital results from this side-to-side overlap of the p orbitals. Okay, which orbitals are overlapping better? The head-on hybridized orbitals or the side-on p orbitals? Which of them have a greater amount of overlap? Head-on. You get these large lobes that overlap more completely. That means that when they're overlapping constructively, their energy drops significantly. They become much more stable. And when they overlap destructively, out of phase, their energy overlaps, or their energy increases drastically because they have more destructive interference. So we find that despite the p orbitals kind of being higher in energy than the hybridized orbitals, the new pi and pi star orbitals are closer to average than the sigma and the sigma star. Okay, we've talked about MO. Do you guys remember what the star indicates? Anti-bonding. So at the bottom, we're looking at bonding orbitals. These are what they're called. This is what they look like. And at the top, we're looking at anti-bonding orbitals. What is the usefulness of an anti-bonding orbital? What does it tell us? How does an anti-bonding orbital work? How does a bonding orbital work? If electrons occupy a bonding orbital, the electrons are more stable than they would have been apart. It's what glues those atoms together in the bond. If electrons occupy the anti-bonding orbital, destabilizes the electrons, breaks the bond. Which of these bonds is easier to break? The carbon-carbon sigma bond or the carbon-carbon pi bond? The pi bond is easier to break? Why? There's two reasons. Take a stab at it. I just enforce the rules. I don't understand them. Less overlap makes it easier to break? Yeah. How come? I think maybe you can steal a little bit of information from this. How do I break a pi bond? You said the pi bond is easier to break. How do I break it? There are two answers. Lower energy input to break it. If I am to donate electrons from something else, let's say a nucleophile donates its electrons to this system, where will the electrons go? They will go to what we call the lowest unoccupied molecular orbital. That is the LUMO. It's one of what they call the frontier orbitals. It's the orbitals involved in the reaction. The lowest unoccupied. Well, where else would electrons go? Electrons can't go into the sigma MO, that's full. Electrons can't go into the pi MO, that's full. Why would electrons go into the sigma star? That's higher energy. Electrons will always fill the next lowest available orbital. Make sense? And that is pi star. Pi star accepts electrons first, so the pi bond is more easily broken. There's another way that we can explain this. What if I have an electrophile? That's something that has an empty orbital or partial positive character that wants to accept electrons. Where would electrons come from in my alkene system in order to attack an electrophile? Can they come from the empty orbitals? No. Would they come from the lowest energy orbital? No. Instead, they come from the highest occupied molecular orbital. Electrons leave the HOMO and go towards the electrophile. There are two reasons why the pi bond is more reactive than the sigma bond. Its electrons are in the HOMO, so if any electrons are going to leave, it's the pi electrons. And its pi star orbital is the LUMO. So if any electrons are going to be accepted, it's the pi bond. I'm sorry, if any electrons are going to be accepted, it's the pi bond that will break. Those are the two reasons. When you get into OChem 2, for instance, my OChem 2 class, the rest of the semester, we're looking at carbonyls, CO double bonds. There will be a lot of CO pi bond breaking, and it's all explained by the LUMO. The carbonyl accepts electrons, and the easiest place to put them is in the pi star orbital. So the pi bond breaks over and over and over. You guys will be doing a lot of alkene additions, which means we'll be taking electrons from the HOMO, and we'll be showing them acting as nucleophiles from the alkene. Okay, so I realized I was a little bit clumsy with this diagram. I gave you one that was partially filled out with some of the verbiage, and then I gave you one that was empty, but it had the symbols. That was so that you could work at connecting the groups. You see here that the higher energy orbital is pi, not sp2. I'm sorry, not pi, p. sp2 is lower in energy. And yet, it is the sp2 orbital that has the lowest low and the highest high. It's the p orbitals that do not stabilize as much and do not destabilize as much. So I wanted you to have some opportunity to say p orbitals create the HOMO and the LUMO, whereas hybridized orbitals create the lowest occupied and the highest unoccupied. All right, now we should recognize that in this pi MO, there are two nuclei. Those two nuclei are not free to spin. If one of those nuclei spun around while bonded to all of its other groups, its p orbital would flip. What orbital is that? Pi star. Congratulations, you just broke the pi bond. There is no pi bond anymore, and you have set these electrons free. They don't know what they're doing. They don't know where they are. What you've done is you've taken electrons from the HOMO and you've pushed them up into the LUMO, creating a vacancy down below. That's very hard to do. It's incredibly hard to take electrons up and leave a gap beneath them. Excitation of electrons. So in one way, you are both breaking the bond and requiring a lot of energy to do that. That means that this is essentially forbidden. You cannot rotate around a pi bond. So, if your alkene has two groups oriented in a specific direction relative to the alkene, and you want to get the alkene to orient those two groups differently, aka spinning around this axis, that would take a lot of energy to do. And for all intents and purposes, you will probably never do it. Not in the lab downstairs, probably not in your bodies, not unless you go to work for some big food processing plant. And the reason I say that is because if you've learned about unsaturated fats, sorry, it's not showing up well. This is called a trans fat, a trans fatty acid, and this is called a cis fatty acid. Cis fatty acids are made in nature, and they're generally good for you. Your body can process them and handle them better. Trans fatty acids are not made by nature. Instead, they're made when these food processing plants put your oils under high heat and high pressure to such a point where they actually push your pi electrons into the pi star. They break the pi bond, they allow it to rotate, and then it falls back down into a lower energy. And your body can't process it quite as well. Your body can't store it quite as well, which is why you have to look out for trans fats, but you don't have to look out in the same way for cis fats. Your body evolved to process this. Your body did not evolve to process this. And so in general, we say this is forbidden. We don't make this happen in our organic chemistry class. You can make it happen. It's very energy intensive. In general, we will not allow it. Is that okay? There's a connection there to your real world about how MO theory explains the production of trans fats and why you now have to watch out for the food labels of what you eat. I just connected MO theory to your food. Love it. What this sets us up for is structural isomerism. Sorry, not structural isomerism, stereoisomers. So we'll go from stereoisomers, and we'll cover this with nomenclature. At the bottom here, I've got this this little line. The nature of the pi bond impacts two things. We saw that it impacts reactivity. The pi bond will always be the first to break, whether it breaks as the electrophile or whether it breaks as the nucleophile. And because these two alkenes are different and they don't readily rotate into each other, I did a bad job of saying this. I said spin and I wanted to put an X. No spin. You can try to make it look like it spins, but you're not going to be able to spin it. That means we need to be able to describe these two alkenes differently. So not only does the nature of the pi bond impact how it reacts, the nature of the pi bond impacts how we name alkenes. We're going to have to be specific about it. Let's take a little break though. 5 minutes, we'll come back in and we'll talk about the nomenclature that we'll use to describe the stereoisomers. We'll come back at 6:10.
Felt bad for teasing on this one. Is it mono? I'll try that.
It is mono. Yes, you did. You don't have the R. You haven't shown whether it's R or S.
Oh, okay. I think I need to flip it. Or wait.
Well, you just need to add a wedge word.
Right.
It's totally.
Yeah.
It's either one right now.
Yeah.
Actually, I told you guys in class that when it's not indicated and you just have a flat line, it's neither. Like not enough information provided.
True. I
Um,
think you did say that.
a colleague of mine though said that if it's flat and it's chiral, it means it's both. It's R and S, not not neither. I said it's like not enough information. He says, and he teaches his class, he says that's both. And if you have a squiggly line, not a dash, not a wedge, but just like a squiggle, it means undecided, not sure.
Oh, okay.
That would be like not enough.
I was gonna say both and neither kind of seems like the same thing in that situation, but I guess not so much.
Yeah, because you can have like a 50-50 mix of enantiomers, that'd be the flat line. Or you could have, I don't know, maybe it's all, maybe it's the other, maybe it's some mixture in between.
Okay, so that's my configuration.
Yeah,
You have to.
then it's just that.
Okay.
A lot of it, I always try to see like what I do know. A lot of it is just review from like applying what I already knew to like it's just having carbon.
Oh, I haven't heard of what it is.
Hmm? I just watched the internet. All right. How should we name our stereoisomers? I didn't give you guys a choice last time. I told you that chiral centers will either be called R or S. That was it. Actually, we also had a similar, we called some enantiomers plus and other enantiomers minus, depending on their optical activity. We didn't talk much about that, and we never actually assigned it because you need an optical instrument to determine that. R and S, you can decide by each carbon just by drawing it on the paper. But what would you name the stereoisomers of alkenes? I already gave a hint about it when I talked about the fats, but it's your choice for now. What would you use to distinguish alkenes from being oriented one way relative to an alkene or the other way.
Would this be the one that's kind of facing the same way, whereas trans is the appropriate one?
Okay, so a cis orientation has zig-zig, whereas a trans orientation has zigzag.
Sorry, I didn't know how to explain that.
No, I get it. That's the appropriate one. All right, now you're just going with cis and trans because it's in the textbook. I already referred to it. Would you accept that? Cis and trans, do those make sense? We've used cis and trans for other stereoisomers, right? Like di-substituted rings. You can have cis 1,2-dimethyl cyclohexane. You can have trans 1,2-dimethyl cyclohexane. Although actually trans 1,2-dimethyl cyclohexane is either 1R2R dimethyl cyclohexane or 1S2S dimethyl cyclohexane. And it doesn't differentiate. So trans is a relative stereoisomer on rings. Cis, not so much. If there's any sort of like meso character, cis can be relative as well. Cis and trans do not always tell you the absolute configuration of your carbons. They just tell you the relative configuration of the groups. Does cis and trans here feel absolute or relative?
I feel like with OCHEM you can always continue to describe it.
You can always get more specific.
Always.
Well, let's look at what rules we have to follow in order to call it cis or trans. Any other terms that you would have rather given rather than cis or trans for their orientations? Okay, well, you'll have to get familiar with Z and E. These come from the German. Anybody here speak German? I don't speak German, so I'm not even going to try to repeat them. But E is, you speak German? Yeah. E is Integegen. Oh, thank you. Which means enemies, they oppose each other. No?
Close enough, yeah.
Okay. And Z, I don't know actually. I don't think it's like the same suffix. Zittegegen? I don't think it is. I remember Z because those things are on the same side. And listen, as long as you've got a funny, silly way to remember one thing, the other one is just like, whatever. So, Z is on the same side. E is they're on the opposite sides. But what are they? What are the things that are on the same side or on the opposite sides? We're looking for high and low priority on both carbons. Remember, for chiral carbons, we looked at 4 priorities. Highest priority to lowest priority on one carbon. This time I'm looking at 2 priorities, high and low, but I need to do them across both carbons because the orientation of these groups is relative to the alkene. So I need to find 2 high priority groups, and I need to find 2 low priority groups. So when we say the same side, we're talking about the high priority groups are on the same side, and the low priority groups are on the same side. But you know what? There's a couple of ways to dice an alkene, and I've seen students get confused about which way should I dice it. If you cut through the alkene, a line parallel to the double bond, then the low priority group of one carbon should be on the same side of that dotted line as the low priority group of the other carbon. But one way that I like to go through this is I'll draw an arrow from low to high. Although I have students that draw it from high to low, it doesn't matter as long as you are consistent. If I draw an arrow from low to high and they point in opposite directions, then it's an E configuration. If I point an arrow from low to high and they go in the same direction, then it's a Z configuration. What rules should we follow to determine the highest priority? We'll use the same ones. By mass at the first point of difference. So I've already assigned on these compounds what is high priority and what is low priority. But if I go in and explain a little bit more, yes, this carbon of the alkene is bonded to a hydrogen and a carbon. And I have to do this for both groups. But this carbon of the alkene bonded to a hydrogen, low priority, a carbon, high priority. Now, we talked earlier when we did nomenclature about how certain functional groups change the suffix, and depending on where that functional group shows up in the carbon chain, I need to describe that functional group with a locant. I need to describe where it is in the chain with the locant. So both of these compounds that we've drawn, they're both 2-butene or but-2-ene, but they're not the same compound. And this is where we use E and Z or cis and trans to describe which stereoisomer we have. This compound here is named Z2-butene, although you can also call it cis-but-2-ene. Those would be equally accepted names. Can every carbon be described by R and S? No. We know of achiral carbons that do not have 4 distinct groups and cannot be described as R and S. Can every alkene be described as E and Z? No. Because not every alkene has a high and low priority on both carbons. Take, for example, this compound here at the top of your nomenclature list. One carbon is bonded to 2 hydrogens. Which one gets high priority? Right. Doesn't make any sense. Which hydrogen is higher priority than the other hydrogen? Sure, this carbon has a high and low priority, but these two do not. So, not every alkene has stereoisomerism. What we can say is both carbons must have 2 distinct groups. This compound at the top of your nomenclature list, on the top right, 3-methyl 2-butene. I'm sorry, 3-methyl 1-butene. No E, no Z, no cis, no trans, because it doesn't exist. It's just one stereoisomer. We say that you can switch stereoisomers by changing the position of any two groups on a carbon. We said that with R and S. We said if you take two groups bonded to a chiral carbon and you swapped their positions in space, you would invert the chirality. You would go from R to S. And the same is true here. If I swapped my methyl and my hydrogen on one of these carbons, I swap the stereoisomer. And that's another thing we can prove here. What would happen if I swapped the two hydrogens? Nothing. It's not a different stereoisomer. It's the same compound. What would happen if I swapped the hydrogen and the isopropyl group? Is it a stereoisomer now? All I have to do is flip this like a pancake, and it perfectly superimposes back on the original compound. Stereoisomers, you cannot rotate, you cannot twist, you cannot flip in any way that gets them to superimpose, and these two can be superimposed by flipping. So they're not stereoisomers, and again, that's because one of the carbons does not have two distinct groups. So this alkene is not a stereocenter. You guys remember this equation where we said we could look at a compound and say that the number of stereoisomers is predicted by 2 to the n? N used to just be chiral carbons, but now N is also these alkenes, these stereoisomer alkenes, alkenes that have both a high and a low priority group on both carbons. So take, for example, this second to last nomenclature. SZ. That means there's one chiral carbon, it has the S configuration, and there's an alkene that is a stereoisomer in the Z configuration. How many other versions of this compound are there? Well, there's a chiral carbon and there's an alkene stereocenter. That's N equals 2. So there are 2 to the 2 stereoisomers of this. 4. I could have SZ, I could have SE, I could have RZ, I could have RE. All of those combinations now exist for my compound, both chiral carbons and alkene stereocenters. So we have to be careful to name stereocenters when they are relevant. Except rings that are smaller than 8 carbons physically cannot get their bond angles to be E. They cannot get trans alkenes. So rings that are smaller than 8 are always cis alkenes. They're always Z. But we don't name that because it would get really boring. And it's understood. You cannot get the bond angles to work out for those alkenes in rings that are too small, so you just don't say it. That's why you'll notice When you go through and you name these compounds, you won't have to describe it as E or Z in the alkene. You won't have to name it as cis or trans. And in this last one, I've got a diene in a ring, and it doesn't have E or Z in it. You won't see it. And is that okay with you guys? You can try drawing an alkene that is trans inside of a small ring. The angle strains are tremendous. Even sketching it on paper, it's like hard to draw. It looks ridiculous. That's trans-cyclohexene, right? 1, 2, 3, 4, 5, 6, 7. No, that's cycloheptene. But the bond angles look crazy. And what's going on with this bond length? It's half the length of the world. So we don't have to name it inside of those. Deal. All right, one last thing to talk about with the nomenclature. This is more of a reminder. Locant set priority. First, alcohols, then alkenes or alkynes, they're tied, then alkyl groups and halogen groups. So if you're going to name a compound with an alkene and no alcohol, that's where we are right now. Prioritize giving the alcohol the lowest locant set that it can have. Prioritize the direction of the linear chain so that you get to the alkene first, or start in the ring on an alkene. You must count through an alkene. You cannot start at one carbon of the alkene, like in a ring. Start at one carbon of the alkene and then go around until you hit the second carbon of the alkene. If you start at a carbon in the ring, at an alkene carbon, you must count through that alkene in order to continue. That seems fair, right? Now, in my opinion, it wouldn't be so far off for IUPAC to come in and say, give a locant for both carbons of the alkene, but instead IUPAC says, just give a locant for the first position, and then we assume that the second position is also the alkene. For instance, we named this as 2-butene. What carbons are involved in the alkene? Carbons 2, obviously, and carbons 3. We don't specify that carbon 3 is a part of the alkene because we count through it. So we hit the alkene at carbon 2, and the alkene continues at carbon 3. And then the last thing I want to give you about nomenclature is multiple enes. I don't know if syntax is the right word, but like the nitty gritties of the name, they get an A back in their name. So you remember hexane, A-N-E is telling us that there is only alkane functionality. Hexene is telling us that there's an alkene functionality in it. But if you have multiple alkenes and you have to say diene or triene or tetraene in the suffix, it feels weird to go from a consonant like X to a consonant like D or T, so we put A back in there. So we get something like butene, butadiene, hexene, hexatriene. Is that okay? It's a little weird. But I don't know. I think these people came up with their rules about how it flows off the tongue. So try saying butadiene instead of butadiene if it sounds better. Okay, so I want you guys to have some time to work on nomenclature. So right now, this sheet is yours. I would say sprinkle in some of the drawing it by its name with naming it by its drawing. Make sure you can do both. Maybe instead of going down one row, going down one column, go across in the rows so that you get good practice doing all of it. All right? I don't want to spend the rest of the time on this, so this is a good exercise for now. And in about 10 minutes, 12 minutes, I want to bring us back in so that we can talk about some stability trends as well. We'll wrap up with stability today. All right? I'm here to answer questions that you guys have as you work on it. Absolutely. Especially if you go in and you show them and give examples. Have you seen that, by the way? Some of the open tutors have taken this so they know exactly our brochures. Down here, picture of them if they're like, well, I don't think I can talk to you over here. You'd be like, yes, please. Up to half. So doesn't mean you'll earn all up to half, but it's about how well you describe it. And so it really helps people that have lower scores on the exam because they have a lot of really good backup. That's really impressive to master that. But here's the deal. Those concepts don't go away. You're going to see some of these things that you figure out down there. So you got to figure out what you got wrong, why you got it wrong, and how to transfer it correctly. Yeah.
what is the right answer, why is the right answer right, and why is your answer wrong, and bring it to the STEM center and say, does this make sense? Did I explain this well? Am I missing something? And then they might be able to say, oh, that's your thought process. Yeah, try to think about this. We forgot this piece of it. Because they might not help you and say, well, here's how you should think about it, and they might you just say, and yeah, and if you don't have time to get it all done, you know, it's always going to increase. Right? But you can just like bring in what you can get started on. And focus maybe on the reflection later and bring them the explanation next. Yeah. Good. Good. You're welcome. You say 1, 3, cycling. Oh, I guess it's 3. 5. Don't do 6. Yeah. No, because you're gonna prioritize both alkenes over alkenes. So you might, you could do it this way. Or, so you said you could also do this way. Think of another. Yeah. And that just makes it.
Yeah. Okay. Thank you.
You're welcome. So you do it. Yeah. That's correct. Die substituted. And even if it's diene, you have to describe both alkenes separately. How's it going? Are some of them hard? Which ones? Oh no. Well, so far you're doing great. There are 2 places. There are 2 places. Like it can be 2-butene or it can be but-2-B. They're both right. IUPAC only accepts it right before the suffix. But IUPAC is on it, like, I won't even speak in French. They're just little bits. I had a few words I probably shouldn't say. That explains how I really feel. But this is great, yes. That's exactly it. I agree, although there are times it does sound better before you It's very descriptive. Leaves less room for error. But I agree with you, it sounds funky. Coming out of the mouth sounds weird. So far, so good. You tell me. Yeah, think about your common shorthands. Methyl, ethyl, propyl, butyl. Is it methyl? Is it propyl? I'm not even gonna buy that. I don't believe it.
Has anyone ever tried to like get those just to match the rest of the menu? Has anyone been about like
No.
tried over.
No, I don't think anyone has. And I'll be honest, I don't know why it started, like why they chose Meth F Pro View.
Because you would think like somebody would like, hey, shouldn't we like
I just noticed too, there's a link up through the and there is no two carbon chain. There are two one carbon chains. Yeah. No, okay. But before you really corrected it, I want to talk to you about the one product. I think you can get a lower load. Yes. I think you can keep the 100, but you can get a lower load. Yep, there you go. So now think about that when you're doing the one below it. How can you really get the lowest locus set? Okay. Yvonne, you're making good progress. Where are you feeling stuck? This one is almost right, except you've got 3 carbons. And that tells me that there are 2. So actually this, yep, just the double bond and then to bromine. Remember we had vinyl chloride before? Yeah, it's that. That's exactly it. This one's right, by the way. Sorry. I didn't see this. Yeah. Yes. In a ring, actually, you don't even have to say it. Yes. Yep. In the same way that we have like bromocyclohexane, and I don't have to say one bromocyclohexane, because I don't have to describe where it is. I can just say cyclopentene. You wouldn't be marked off, yeah, but you might not see it either. Yeah. Although in the one below it, I would recommend adding the locus for it. It does just help when you've got more complicated things going on. Technically, it wouldn't be required, but it's helpful. Yeah. Or you can call it one cyclopentene as well. Yeah. Nothing wrong with it. It would be wrong if you called it 2 cyclopentene or 5 cyclopentene. This one though, we can actually get a lower locus set. We can keep 1 cyclopentene and we can get a lower locus set. Yes. And then with the one below it, I think you started numbering here. 1, 2, and then you came back around to the second carbon of the alkene. It's not allowed. Or 1, 2. If you start here, you get 6 atoms. But if you start here, you get 3 atoms. But either way, we have to count through the alkene.
All right, I want to talk to you guys about a few of these, and then also just talk about some stability trends so that we have something to pick up on with Wednesday. You guys had some good points. Cyclopentene is a correct name here. You don't have to say 1 cyclopentene because there's nothing else going on. Then with the rings, what I noticed is that it's mainly an issue of finding the lowest locant set overall while prioritizing the rings. So remember, I'm not allowed to start at one position on an alkene and then come back to the other position. I have to count through that alkene regardless of which direction I go. And with a diene, I want to minimize the locant set for both alkenes. So I'm going to count through the alkenes consecutively, whichever way I go. But I want to find the best route that minimizes the locant set for everything, especially on an alkene or on a ring, where I can kind of decide where to start and which direction to go. On linear chains, it's a little bit more straightforward. It's either from the left or from the right. And if the alkene has a lowest priority, a lowest position from one direction, doesn't matter what anything else is, that's the direction you go. But if it's tied in either direction for the alkene, then you go for the lowest locant set of whatever else is there. So if you ever run into a tie, oh, the alkene is 3 this way, the alkene is 3 this way, then look at what helps the next locant set otherwise. Okay, alkenes are actually not all equally stable. We can rank the stability of alkenes. Stability here means just energy, right? Lower energy alkene, less reactive, easier to form. So I'm going to mark this as an energy diagram going up in energy. At the highest are mono-substituted, and at the lowest are tetra-substituted alkenes. We'll talk in class on Wednesday about stability of some other groups as well, and we'll try to rationalize why the tetra-substituted alkene, why the alkene that has more carbon groups pointed at it is less reactive, and why the mono-substituted is so much less stable, why it's so much higher in energy. Then, of course, we know that the tri-substituted is down here. And when it comes to di-substituted, there are actually 2 things I want you to see. No, there are 3 things I want you to see on the di-substituted. First, the lowest, I don't actually have a good way to describe this. We might say like a single branch. The lowest in energy, the most stable, is that single branched alkene where the 2 carbon groups come off of the same carbon. That's the most stable di-substituted. Then we have a trans di-substituted where the groups are coming off of either position, either carbon. And the most unstable, the most reactive, the least stable, cis. So we have a cis di-substituted, a trans di-substituted, and you might call this a single branch di-substituted. Does single branched make sense? Is that weird? I don't actually have a good term for it, but what I'm trying to say is that both groups come off of the same carbon. Can you justify why the cis di-substituted alkene is higher in energy and less stable than the trans di-substituted alkene? What knowledge do you already have about these carbon groups that could help you justify that? What kind of strain? We got 2 types, torsional and steric. You? Torsional? Torsional is eclipsed pairs of electrons. Actually, if we looked at the Newman projections of both of these, we see that they both have torsional strain. They're both eclipsed because they're alkenes. But this group has what else? Steric strain. It's got those large non-H groups next to each other. And this group doesn't have that steric strain. It's got methyl eclipsed with hydrogen. So why is cis less stable? Steric strain. All right. When we come back on Wednesday, we're going to move on to the back side of this sheet. We're going to look at how to make alkenes and how to use alkenes in chemical reactions. It's very possible that Wednesday I'll have another worksheet for us as well, so that we can start diving into, we have maybe a dozen alkene addition reactions, and that's section 8. So we're going to spend the rest of this unit looking at our addition reactions, learning how to predict products, predict reagents, predict starting materials, given 2 of those 3, and how to draw mechanisms for a selection of them. Have a good night, guys. I'll see you on Wednesday.